Having looked at the natural solution, we now look at the forced solutions. We saw that a convolution was involved, and when we went through and we looked at the linear time invariant case, we went through and we iterated. Notice that we were actually using the state transition matrix as we went along. Okay, so as we went through the iteration, x1 is equal to a x0 plus b at u at time 0, which is basically a is the state transition matrix from 0 to 1. Okay, and then when we went to x at time 2, we have a times x of 1 plus b times u of 1. We substitute this stuff in for x of 1, and we get this expression, where we now have phi of 2 in here. And so forth, we continue, and this is the expression we get. So we actually have the state transition matrix appearing, and actually, anytime we see an a in this expression, we actually have a state transition matrix that can be mentioned. So you actually have that. And we'll come back and see what that looks like in a little bit. So, in general, for this forced solution of this equation, we have some initial condition, we have some input. So, in the natural solution, we just looked at the initial condition term. Now we look at the control input term. And so this is the solution that we get. X at time k is the state transition matrix times the initial condition, plus this thing times this thing. What are those things? Well, introducing some new stuff. So if I look at this matrix, if I define it to be this matrix here, b, ab, all the way to a to the power k minus 1 times b, and u to be this vector, this column of elements that go from 0 up to k minus 1. So notice that, remember, we had a convolution sum. This convolution sum can actually be written as this row times this column. So this row is actually a matrix of dimension n by k times m. This column is of dimension k times m by 1. So we actually, when we multiply this times this, we get a vector that is n by 1, which is the same dimension as the state. The state is n-dimensional. So this is the result we get. So we have our state transition matrix, and we have what can be called our input map or our control map. Okay, so we have our control sequence, we have our state transition, so we have the input map, and we have our input sequence, our control sequence. So this is the result that this simple equation, the state transition matrix times u, and the control map operating on the input sequence. So that's actually what we have. So we have a nice compact expression for the solution of this difference equation. What about for the linear time varying case? Well, again, here we have a being a function of time, b being a function of time. We can go through and do the iteration. So we iterate from time t0. So at time t0 plus 1, we're going to get this expression. t0 plus 2, I get this expression that involves t0 plus 1s. This was obtained in the previous step. I can plug all of this into here, and I get this expression. I do the same with x of t0 plus 3, and so notice I'm going to have t0 plus 2's everywhere here, and then this quantity here is represented by this term, and I plug that in and I get this expression, and we can see the number of terms increases rapidly because we can't combine them. Right? We can't combine the terms like we were able to. However, in terms of the forced solution, that we can actually write the forced solution in this way, just like we did with the linear time invariant case, where now we have a different definition for the state transition matrix and a different definition for the control map, but we can still write it in this form. That's the beauty of this state transition matrix notation. So again, the state transition matrix is the product of the instances of the matrix A, and the control map can be written as a product of the state transition matrix times the instances of B, where the state transition matrix also varies. And then we have the control input sequence as we had before. So this is, we can actually write our solution in the exact same form, and so we have that nice feature. So again, here's our forced solution. Here is our control map, our input map. So for an M input system, the input map, which is defined here, is of dimension n by t minus t naught times m. That's the dimension. So what happens if t is equal to t naught? Well, that means this dimension is 0, and that means this guy just basically poofs, vanishes, goes away. So really, we only have the control map if we're looking at some time in the future. I mean, look at ahead, not just at the initial time. Okay. And we see that the dimension of this matrix expands with t. As t increases, the matrix gets fatter and fatter and fatter and fatter as time goes on. So it's not that bad in the sense that it's just a matrix, okay? But it is a matrix that is expanding. So every time we take another step, the matrix gets fatter, and so we have that to deal with. So this is the solution, and this is a look at the input map. The input map also satisfies these what are called composition rules. Composition rules first says that the input map from t naught to t naught is just 0, or actually its dimension 0. So that is, it doesn't actually appear in the solution at that point. If we go from t naught one step ahead, it's equal to the matrix B at time t naught. If we go from t naught to t2, the input map goes from t1 to t2 and from t naught to t1. And so we have these expressions for the input map. So we have a telescoping that occurs in all of this. So this is the composition rules of the input map. And so with the concept of state, again, if we start at time t naught and go to time t, here's the solution. If instead we start at time t1 and go to time t, this then is the solution. That is, we start over at time t naught with we start with this initial condition, and that initial condition is enough to keep track of everything that's gone on from time t naught to t1. And so we don't actually need to know that input sequence that brought us to this point. X of t1 has the information that's needed embedded within it, and so we can actually look at the state from t1 to t, not from t naught to t. In general, we're going to be looking primarily at linear time invariant systems because working with linear time invariant systems has limited usefulness. The only exception is the case when we have periodic linear time varying systems. So up to this point, we've looked only at the state equation. What's going on with the output equation? Well, in general, we can also stack the output equation. If I can take samples, the output value from 0 to k minus 1, that's k values, and I can show that y at naught is equal to c times x naught. Now we're looking at first in the unforced situation. C times x naught, y at times 1 is c times x1, but x1 is equal to a times x naught, all the way down, c times x of k minus 1, but x of k minus 1 is equal to a to the power k minus 1 times x naught. And so notice that x naught can be expressed in each of these terms, and so all of these outputs in the unforced system can be written as a linear combination of the initial conditions. Okay. Linear combination of the initial conditions. And so we can define something called the output map. So the output from 0 to k is this output map times the initial condition, and here's the output map. So we had an input map that involved b, ab, a squared b, all the way up. Here we have the output map, which involves c, ca, c to the power a, k minus 1. And there's a lot of similarities between the output map and the input map, and we're going to come back later and talk about something called controllability, observability, that will actually involve these maps. So that's for the unforced equation. What about for the forced equation where we have an input? Well, in this case, y naught is equal to c x naught, c at times y times 0, c times x at 0, d times u at 0, and so forth. And notice that I don't get an accumulation here. I just get the exact value appearing. Okay, but we know that in the forced equation, x at time k minus 1 involves not only the initial condition, but also the input sequence up to time k minus 1. And so there's actually a's and b's appearing in this expression. And we can go through and show then that the forced response looks like this. Okay, c times x naught. So the output map times x naught plus this guy times the input. So this is what may be called the direct feed-through term. And this is actually a matrix that is sometimes referred to as the system Hankel matrix. It's a Hankel matrix because it has things repeated along the anti-diagonals. Okay, so usually we think of diagonals going one way, the anti-diagonals go the other way, and so this actually has some significance. It's called the system Hankel matrix. So these are the output equations for the forced system. All right. Now, we can actually look at all this, since we're talking about discrete time, we can look at it in the frequency domain as well as the time domain. So we can use the Z transform to analyze this. The Z transform is to the discrete time as the Laplace transform is to the continuous time. And here when we talk about Laplace or Z, we're talking primarily about the one-sided Laplace or the one-sided Z transforms. Okay, that is, we're talking about causal signals or sequences. All right, taking the Z transform, we can use the time advance property of the Z transform that says that the Z transform of the signal advanced by 1 is equal to the variable Z times the Z transform of X minus the initial condition. Okay, now we know that our Z at time t plus 1 satisfies the difference equation. X of t plus 1 is equal to ax of t plus bu of t. Taking the Z transform of the ax of t bu of t, I get this expression, ax of z plus bu of z. I'm just taking the Z transform of these guys. And so we now can solve for x of z. So notice this quantity must be equal to this quantity. I can take the x over to the other side, the x of z over to the other side. And when I do, I can factor out x of z. So I'm missing a step between here and here. I can factor out zi minus a times x of z. Multiplying through by the inverse, I get this expression. Notice I have a z here and an x naught. So I'm going to take this term over to this side, this term over to the other side, solve for x of z, and this is what I get. This is the expression I get. So notice I get zi minus a inverse multiplying both of these terms. This one has a z here because of this. Okay, and so if I take the inverse Z transform of this expression, and if I assume 0 input, that is, if I'm only looking at this term, this is the natural response. This is the natural response of my system. This is the forced response of my system. And now I have it in the Z domain. So the inverse Z transform of this expression we know is a to the power t. And so we have this relationship. The Z transform of the matrix raised to the power t is equal to this expression, Z times Zi minus a quantity inverse. So this is the Z transform of that. And so we have that relationship. Over here now, I have this function of Z multiplying this function of Z. And we know that when you have a product in the frequency domain, that corresponds to a convolution in the time domain. So we're actually getting the convolution, and this is where it actually pops right out. That convolution appears. For the output equation, if we assume 0 initial condition, we can obtain the transfer function. So y of z is equal to cx of z plus du of z. X of z, in the case when you have zero initial condition, is just zi minus a inverse b. And so this then becomes the transfer function. Here's the unforced response, involves the initial condition. And this is the transfer function that involves the input and not initial condition. And so this is the result that I get. So I can define the transfer function. So this is actually going to be a matrix because in general, I can have multiple inputs and multiple outputs. So in general, this will be a transfer function matrix. And this is the response in the z domain. Notice that when we multiply this out and multiply by the initial condition, this is just a column vector. And so this is just going to be a vector function of z. Similarly, u of z is actually a vector function of z. And so this is a matrix. When you multiply this out, we'll just get a column. So y of z itself will be a column in this case and a column in this case. So we now have analyzed this both in the time domain and in the z domain. And so in summary, we have these results. For the linear time invariant system, we have this solution. For the linear time varying system, we have this solution. And so we have the result. So we actually have an explicit form for the solution in the event that A is, that the system is time invariant. And so, but in general, the question burns. How do we compute a to the power t minus t naught? That's a very good question. Stick around and we'll find the answer.